Yeah. So I think you have music playing on your.
Oh, sorry. Yeah.
Alrighty. Okay. So. Okay, so what's the goal of the talk? I'm going to be talking about cohomology. So I guess there's even that sentence doesn't mean something precise, I would say, because what even is the cohomology theory, and even then there's a question about what even that is. But the idea is just to talk about cohomology and see what it is. So first off, what is the goal of cohomology? First, how many here are okay with manifold theory, like the basics? Okay, more or less, that's fine. Bundles are fine, we've talked about that, and what's in cohomology before? Fairly familiar, or just a little bit? Fairly familiar? Nice, okay. So, my goal today is mainly to not, kind of use the realm cohomology, which I guess what most of you are familiar with, to motivate what is sheaf cohomology. And that's why I said that what even is cohomology theory. You have few ways to look at it. The other is Steamroad axiom, which I guess is the most popular for topologists. But you also have the axiomatic sheaf cohomology, which I don't think it lies in the axioms of Edinburgh, if I'm aware. I'm not particularly sure, but it's more algebraic, I guess. So, first off, what's the goal of cohomology? Maybe we know the definition, but what really is its goal? So, the only thing we know to do as mathematicians is algebra, more specifically linear algebra, but algebra in general is the only thing we really know how to do. So we want to reduce our, you disagree?
I think that topology is the thing that I know how to do.
Okay. We all know how to do algebra. So what we want to do is reduce our geometry and topology problems into algebraic problems, because that's a lot easier to deal with. So that's the main goal of cohomology, is to turn geometry problems, geometry and topology problems. So into a certain family of algebraic problems. So, okay, that's pretty cool. How do we want to do that? The idea is, so what does this even mean? It means that if I have some topological space X, then I want to associate to it some algebraic structure, which is known as H upper star X, and it's going to be an algebraic structure, and I want this to encode certain geometric or topological information. Okay, so that's pretty cool. That's kind of what we want to do. And what properties do we want this to satisfy? So properties that we would wish. If you've done some algebraic topology or stuff, even just talking from last week's talk, as Willa mentioned, homotopy groups are pretty hard to compute. It's not easy to do. It sure return a topological problem to an algebraic problem, but it didn't quite help as much in some way. Help in others, not in all of them. So first property we want H star of X to be easy to compute, or easier to compute, as opposed to homotopy groups. And again, we want it to be a functor. So again, who's okay with category theory? What's our front categorical language? Are you okay?
I can just go for it.
I'll explain briefly what I mean. So we want H star to be a functor. The idea is we want to take a topological space. We want to turn it into an algebraic structure, some algebraic object. We want also to map between topological spaces, continuous maps, into homomorphisms of the corresponding structures. And we want to preserve identities. If I have the identity map on X, I want it to become the identity map on whatever algebraic structure I have, a group, a ring. And if I have So identity, I wanted to also preserve composition. So if I compose two maps, I wanted to also be the corresponding composition there, either covariantly or contravariantly, either reversing or not the arrows. So we want that. And maybe, who knows, maybe h star of point equals to 0 for every k equals to 0. Maybe, depending on what your philosophy is online. If you don't have that, I think that's called a generalized cohomology theory. And if you do have that, you get a regular cohomology theory. So it depends on your philosophy. I personally like it.
Do you want your cohomology theory to be homotopy invariant, or will we find some examples where they're not?
So, I didn't put that in the list. Generally, you do want it to be homotopy. Just because homotopy is easier than, like, a lot less restricted than homeomorphisms, but yeah, you want it to be homotopy invariant. So yeah, that's homotopy invariant. Okay. All right. So this is how it should behave. I guess from the fact that it's a functor, we already know that it kind of classifies, or like it detects whether the spaces are homeomorphic or not. Because if it's a functor, then if two spaces are homeomorphic, then the corresponding cohomology groups are going to be isomorphic. So in particular, if you can compute the cohomology groups that are not isomorphic, means that the spaces are not homeomorphic to begin with. So that's one type of invariant we're finding here, whether they're homeomorphic or not. But of course, the other direction is not true. You can have non-homeomorphic spaces that have the same cohomology group. So it's not as a two-way arrow, unfortunately, but it helps at least classify a couple stuff. So the way I'll write this, so what let me put it here. So properties you want, and I'll put a fifth property. So it should contain obstructions to topological or geometric properties. What do I mean by this? I mean that we would like it to have come with statements of the form if, just like I said with homeomorphism, so if h star of x is such that, or satisfies some property b, then x satisfies some property b. So, for example, for the homeomorphism, if h of x, say you have two spaces x and y, if h star of x is not isomorphic to h star of y, then x is not homeomorphic to y, and so on. For different stuff, we can go stuff about irreducibility, about existence of sections, and so on. So, then we wanted to have some useful information. That's the whole point of it. We don't want it to just construct something random that has nothing that is in code. All right. So, how do you come up with a cohomology theory? You guys are physicists, so the most natural one is the round. So, how do you go about it? Just to motivate this a little bit further. So, where do these appear? We have the existence of potential functions. So if I want to find, given the vector field x, I'll use this to denote my vector field on an open set U of R3. So open. So you have this vector field here. Does there exist some smooth function f on U such that x is the gradient of f? And you kind of process this real quickly, how you're going to define your space, your solution space. So if x is equal to the gradient of f, first off, you can try to look at all the vector fields, mod those that are of this form, and you're gonna the non-zero elements of that quotient space are gonna be those that don't have something that satisfies this. But this space is way too large. If you look at the space of all vector fields, it's huge. So that actually reduces space further by noting that if I look at the curl of the gradient, curl of f of x is the curl of the gradient, which is 0. So I can actually reduce from looking at all the vector fields. I can just reduce to those that have 0 curl, and that makes it finite dimensional now. So then, so solution space of this problem is going to be the quotient space, which I'm going to call H1 of U. It's going to be the set of all vector fields U such that they have 0 curl, and I'm going to mod out by the x in U such that there exists an f infinity.
This is always finite?
The way that I phrase it, yes. Finite dimension. Yes. Yeah. The way you prove this, I guess, is it always finite dimension for U in R3? Yeah, it is always finite dimension. Okay. For general, it's change for manifold. But the way you would do it is we write it as a differential form, and by vector fields are in R3 are equivalent to 1 forms. If you want to look at that, so what you're really looking at is the space of all 1 forms omega in on U that have zero derivative, and I'm modding out by those. Such that will make it equal to df for some n.
Are we finding curl because that's like star d star?
Well, the intuition is that d of one form is analogous to curl,
and you get the corresponding point between the star.
Yeah.
True.
Okay.
Yeah.
Exactly.
And finite dimensional here as a module, right? Like, or as a vector space, or
no, as an R vector.
as an R vector space. Okay.
Again, this is really for U and R3. For general, it might not be.
Okay.
Yeah, because it would reduce to the same picture. And H1, at least for you could put space that doesn't manifold, that doesn't have this.
You can use non-compact manifold, like infinitely many donut holes.
Okay, yeah, you're right. Yeah, so for manifold, you know,
If it's compact.
Wait, why did you write f equals to 0 on the bottom there? Shouldn't it be for the x or minus something?
Yes, you're right. Oops.
Okay.
Okay. Yeah, good. So there's that, and now we can kind of generalize this in general by just replacing U by some manifold M. So we generalize, we replace U by some manifold M. Again, you guys are familiar with differential form, so I don't have to go through it. Have a manifold M. The one we can put a K, and just replace all the ones with a K, and this by some lower dimensional form. So omega K M with 0 derivative mod omega K such that omega is the exterior derivative of some K minus 1. This defines our ground cohomology. So I'm going to put a subscript BR because it might be, I'm going to find a different cohomology theory of it, but so these are the round cohomology. All right. So that's all nice. And then we can check that it satisfies these properties we want, right? So the functor, if I have a map between system manifolds, I can pull back forms, and since the pullback commutes with exterior derivative, I've seen a mapping cohomology. So there's that. You can also, just by computing, make sure the pullbacks respect compositions and identities. So that's pretty nice, satisfies the properties we want. And now this one, it's pretty easy to prove. If you have a higher, this is a third-dimensional manifold, So any one form or above is 0, and all. So yeah, so it's going to be 0 for every k bigger than 0. You can compute the 0th one just is going to be r, just because that's a single component. Just put it like that. Because h0 is going to be all the smooth functions into r, from a point into r, and that just means you're choosing a real number. It's going to be r itself. Okay, we're good about that. All right, that's pretty nice. Now let's do a quick computation, and as I go through this computation, I'm going to start introducing more definitions, so that we can talk about this later. Okay.
See how is it visible, the time on the right, is it visible?
Yeah.
Okay.
So what we're going to do is we're going to compute the cohomology of r to the n real quick, and we're going to do something more general, but it gives us that result. So first, let's consider the following product: m cross r goes into m. We have this projection map into the first component, and since I have a vector bundle, I can choose a canonical S of 0, a section, which is going to be the 0 section. This is a nice one that's preferred. And since S0 is a section, we have that phi composed with S0 is the identity on M. Since particularly cohomology is going to mean that the identity map on the case cohomology of M is going to be the same as S0 pullback composed with phi pullback. These are the pullback mechanisms.
Can you put a little bit more pressure in the chalk? It's kind of hard to see.
Sure. Actually, I'm going to take a different chalk because it's not
yeah, it's not very visible.
Probably quality chalk. Okay. So because we have this, means we have a one-sided inverse, and there's the question if we get the other side of it there. So is it true that I have also the following question mark identity in HK of M cross R? Is it true? And the third part is yes in cohomology, but not in forms. So let's actually find out what does it mean to be identity in cohomology in this case. Okay, because let's remember that cohomology, first we're looking at closed forms. So at the level of forms, it's not going to detect, so at the level of cohomology, it's not going to detect closed forms. And since I'm also modeling out by exact forms, in cohomology we don't detect exact forms. So what do we want? What is the goal of this? Is to say that we don't need to prove, so at the level of forms, you can actually show phi star composed with S0 star is not equal to the identity on the K forms. But that's okay, because all we need is some K, some map K from the K forms of M into the K-1 forms of M, such that if I do phi star S0 star minus, or let's do identity minus this, I want this to be equal to some plus or minus, doesn't really matter, K times the exterior derivative minus the exterior derivative and K. The idea is now, if I take a form, you're going to map it here, and then the derivative is going to make it exact, so it goes to 0 in cohomology. But if I take a closed form, then this is 0, so I get 0 here at the level of cohomology. So what we need is, we don't need this at the level of forms, all we need is some K that satisfies this. And if we manage to find this K, then actually we get this identity cohomology. Does that make sense?
The composition on forms, is that just take your form, look at what it's doing in the 0 section, and kind of regularize that?
Yes. pretty much what it's doing. So yeah. Okay. I don't know what you mean by regularized. Sorry.
It's just not a precise word. Like it just makes a constant on the fiber.
Yeah, pretty much. Yeah. Okay.
Sorry, why does the minus term go away when we're talking about cohomology? Like the in the bracket.
Here?
Yeah.
Oh, so this one here?
Yeah.
Because if I have a form, I'm going to map it here. I'm going to have a k-1 form. Then I'm going to have a k form again, but it's exact. It's going to be d of something to sigma.
Makes sense, yeah. Got it.
Okay. So we have that. So that's what we want to find. And it's actually not so hard to find this k. And I'm going to prove that it's... Okay, first off, I give a definition first. So, because I actually want to give this k a name. Definition. Okay. We call k a homotopy operator between the identity of k forms and star. And if you replace this identity by some other map of k forms, and this by some other map, you just say a homotopy operator between f and g, where these are maps between the chain. Okay. And okay, so our goal is to find this homotopy operator between these two, and I'll give you the formula. So actually, I'll motivate a bit. The formula way is this, but yeah. So if I have a chart, an atlas U alpha, phi alpha, is an atlas for M. Then again, an atlas U alpha cross R, phi alpha cross identity, is an atlas for M cross R. So locally, all my forms that this means, we better this locally a K form on M cross R is of the form, I guess it's a linear combination of an R linear combination in this case of one of these two forms. So either it's going to be phi star phi and some function f x comma t, or something of the second type, which is going to be phi star phi, the pull back of some form on M, then I'm going to have x t dt, where phi is k. So in other words, it locally looks like something in M, which something in R, or maybe doesn't have an R component. Okay, and once you see this, your first thought, if you have a form, the first thing you want to do is integrate it. So that's what they're made for, might as well do it. So we define K, this implies that we're going to find K on the first type to be pi star pi. F is going to be 0, because we have nothing to integrate over K. And, over R, sorry. And for the second one, pi star, the phi. F, here I have a dt, so I can integrate over R. R, so we're going to have pi star phi. I'm going to integrate the second component. So R. So this is going to give me a k-1 form. So I'm going to go from k to k-1. I can get rid of that R component. That gives me 1 degree less. And you can actually show that this is the homotopy operator. So this is well defined on all the forms, and it's a homotopy operator. So in particular, we obtain our first result on cohomology.
Sorry, what specifically is the operator?
K.
Okay. Okay.
So I define like this on each one. Each one's linear combination, so I just extend it. So what do I get? The corollary, the direct cohomology of the M plus R is the cohomology M, and in particular, if I choose M to be Rn, I'm going to have an Rn plus 1 is going to be the cohomology of Rn, and so on, 1s, 1s, 1s. In particular, I also get cohomology of R to the N is the cohomology of points equal to 0 and R other points. So it's equal to okay. So you have that, and not only that, but if you look at the proof, all I needed was a section. That's all I really needed. So in particular, a section, and I guess the fact that I have a trivial part there, otherwise it's a bit more complicated. But the same proof, if you choose different sections, is homotopy invariant. So if F and G are homotopic, then they use the same mapping cohomology. The idea is if you have a homotopy between the two, you're going to be a map from M cross R into N. And by taking the 0th part and the 1 part, the one that fixes like at time 0 or at time 1, you're going to have these S0 and S1. And these are going to be inverses of the projection onto M. I can write down if it's not particularly clear.
The sections are the 1 and the 0?
Yeah.
Okay.
So you have the 0 section into M cross R, and the 1 section into M cross R. And these are going to be inverses of the projection map by this proof.
So can you just write?
Yeah, I'll write it down. Thanks. So what I have this homotopy H M cross R into N. I have this projection map pi into M. I have two sections, S0, which maps into x comma 0, and I have S1 into x comma 1. And these two cohomology are the inverses of pi, just by the proof that I gave. But then, so I have this. So since they're inverses of pi, inverses are unique, so S1 star is the same as S0 star. The inverses of pi star, they're both inverses. And inverses are unique.
So what is the inverse of pi?
In cohomology of pi stars, the inverse is going to be S1 star and S0 star.
So you still have to like invoke the composition to get from M all the way to N.
Yeah.
Show that F and G are actually the same. So,
Yeah. Because it's only a right inverse, right?
No, okay, that's just by this part here, this same proof, I have a trivial bundle over M, the M cross R. By just replacing S0 by S1 here, I can do the whole same thing. And this is always true for S0 and for S1. Now here, I can choose my same homotopy operator, right? So I'm going to have this other side by just replacing S0 and S1. So what does that mean? It means that S0 star is the inverse of pi star, the full inverse, not just one-sided inverse.
Oh.
But I also have S1, I can do the same argument. I'm going to have S1 star is the inverse of pi star.
What is another pre-image? Why is it an inverse?
By this part, like that's what I'm explaining right now, right? It's an inverse. Like I'm not sure I understand the question. Like
the part I don't understand is why is it an inverse and not a pre-image?
Like a pre-image is not a map, an inverse is a map. So I have these two sections, right? These are maps.
Yep.
So S0 of x is x comma 0. S1 of x is x comma 1.
Yes.
So these are maps.
Sure.
And what I'm claiming is that if I take the start of this, if I go to cohomology, I get maps in cohomology, and I'm saying that those maps that I get are inverses of phi star.
Okay. Okay.
So you don't need any pre-images here. There's nothing happening there.
Okay. So this whole thing, we never had pre-images?
No.
Okay, that were all inverses?
For that one, yes. This is a full inverse.
Oh.
Like, well, I'm not exactly sure what you mean by pre-image, though.
Yeah, that's what I was gonna ask, if you can explain what he means.
Yeah.
Kids by
Well,
not having
because-
any periods. I've
Well,
never heard of this in terms of periods.
Because pi is not injective, right? It's surjective. So, but like,
But we're talking about pi star, which is like, yeah, they're maps on cohomology. And then
like we pass from the topological context to the algebra context.
algebra.
Oh, okay.
So they're like group homomorphisms. Like,
Yeah.
okay, sure. I was thinking of in the topological context.
Okay. Yeah. So S0 star and S1 star are both inverses of phi star, full-on inverses, so they must be the same. The inverses are unique. But we know that F is equal to H composed S0, G is equal to H composed S1. And if I take star everywhere, I'm going to have S0 star composed H star, but S0 is equal to S1 star, so I get equality. So we get homotopy invariance of the round cohomology. All right, that's pretty sick. And you can do more stuff because of this. You can have a deformation retract. Then the cohomology of the subspace is going to be the same as the cohomology of the total space, and so on. I'm not going to elaborate on this. I don't know what the deformation retract is, but you get all this. Okay. So I have a bunch of properties. I showed homotopy invariance, cohomology of a point. It's a functor. There's the other part is whether it's easy to compute or not, and that's kind of the useful part, I guess, if you're a physicist, because you want to know how to compute these things. And I read that board, but I think it might be good if I just restart at the beginning, because this is probably one of the most important topics in the round cohomology and cohomology theory in general, and it's what's going to motivate later on my definition of check cohomology. So let's talk about that. And it's the Merritt source. Okay, how do we go about this? Let's fix this new manifold M. I'm doing everything on manifolds just because they're a bit nice to behave, but you can generalize this to a certain extent to other types of spaces. And I'm going to assume that I can write it as a union of two open sets. So you're going to be our open set. Then I can make this diagram. I'm going to have the intersection of the two open sets. I can include into U, or I can include into V. Then I can include into M, and I get this nice square. Now what I can do is I can take H star of everything here, and I'm going to have a diagram with the opposite arrows. The arrows reverse with H everywhere. And what I'm going to do is I'm going to collapse this to a single piece by taking the direct sum of both groups. So what I mean is I'm going to have a sequence H star the round M into H star the round of U, H star the round of V, and H star the round. Sorry, let me do it at level forms first. We've also done it as cohomology, but that's not useful for us right now. That intersection. And then we get a short exact sequence. So you can try the sequence short exact, where what I'm doing here, if I have a form on M, I'm restricting it to U, and I'm summing it with the restriction to V. So that's nice. And this last map here is going to be the difference. You have omega and tau. I'm going to map it into the difference between these two. After restricting. I'm using notation here, we have to restrict them to the intersection and then take the difference. But you can show that this is short exact. Do this computation. So what do we like about short exact sequences? The induced Coulomb exact sequence cohomology. So when you have this, then we have seen a long exact sequence cohomology. That's here, HK of M to HK. HK of V. I'm running a bit out of space here, but this is part. And then so this is the sequence is exact, so you go all the way until H. You should start at 0 first. So you start at 0, H0, then you go all the way there. So you can see. So this is exact, and because of this, you cannot compute your cohomology as long as you have your U and V being nice enough. So if you choose in manifolds, you have these charts that are homeomorphic to R to the n, and you can compute those. So if you manage to find some nice enough open cover, then you can actually compute this directly, because you know what HK of U is and what HK of V is. And there's also this other extra condition, because maybe you know how to compute HK of U and HK of V, but you might struggle with this one. So you want to choose it so that U intersection V is also nice enough. And this motivates the next definition of a certain type of open covers that we like, and usually have them. Not usually, you always have these. Definition: a good cover M is an open cover UI and such that first each UI is diffeomorphic to Rn, but not only that, every intersection UI1 intersection to UIK is diffeomorphic to Rn as well for every K. So these are called good covers, and you always have them actually. I think for a more general topological concept, you have this idea of contractible covers. That's what you want to use. You want to use intersections to always be contractible. But for manifold theory, you have these, and actually they're cofinite in the category of open covers of your manifold.
Sorry, so what's with the I subscript? What's I sub 2, for example?
It's just choose K elements of big I of the index set. Choose K elements.
Oh, okay. That's
Just
okay.
You do this so that you have a trivial cohomology in the. Okay.
Exactly. So the goal is that you can actually compute every single one of these except for HK of that.
Okay.
Yeah.
What's cofinite?
What's cofinite? I'll let you Google it. The idea is, I'll say it like this: you can always, if you have an open cover, you can always have a refinement. So you can make more open sets. You can break each of it into smaller ones, and you can always do it so far enough, take more and more refinements until you have one that's satisfied.
Okay.
Yeah.
That's cofinite?
Cofinite for this, yeah.
Cofinal.
Cofinal, sorry, yeah, not cofinite. No, cofinite is something else, sorry, cofinal.
Cofinite just means a complement is fine.
Yeah.
Okay.
Like a different thing.
Okay. Is
Yeah.
that what you said?
No, cofinal.
Right.
Yeah. So you have final objects. In some categories, you also have cofinal, which are dual objects. In this case, it's cofinal.
Okay.
Which are not the same as terminal objects.
No final object.
Like, or assume cofinal would mean initial, but I guess not. Actually, no, I'm not.
I'm not sure if it has a categorical context. It's just like if you have a sequence and the subsequence is cofinal, it like extends arbitrarily far down the sequence.
I see.
I don't know if it's a category.
But you can always make it like if you have a directed. Basically, you do not write a directed set, right? You can think of like. I'm pretty sure you can probably cook it up. I don't think it'd be that bad. Because you can have you can make it into a diagram, right? You have a directed plate, you turn it into a diagram by taking a vector, and you can just already there. I'm not sure if actually would coincide with the initial. I feel like it should. I'm not sure now, but I'm not a category theorist, so I'm not going to delve into that. Okay, so now that we have this, which is the most powerful tool for computing cohomology, and let's abstract this into making something more interesting.
You don't want to compute for spheres?
Sure, we can compute for spheres. Let's do an example. That's actually when I was doing it. And it's like I lack a lot of examples, but let's do an example. So this is going to go off the books. But suppose you have a sphere. So for Sn, I have two open covers. So the one we're going to take, well, actually, no, we have one open cover, which is by the stereographic projection. So we have an open set U and V given by stereographic projections. I'm not going to define these because we don't actually need to know what these maps are. But the main point is that let's make it into a picture. If I remove this point, that whole part is going to be U, so it's 1 point removed. And I have this one. Let's take away the south pole, it's going to be my V. And if you intersect it, U intersection V, that's going to look like
The sphere of one dimension.
Yeah. So there's, it's going to be R to the N minus the origin. It's going to be converted to this, which is homotopic to S to the N. Okay, that's perfect. So now we can put it into our main arbitrary sequence. We're going to have 0 into H0 of S to the N into H1. This is up to N, so H0 of U, which is just Rn, H0 Rn, and we're going to have H0 of S to the N minus 1. So you go to the kth one, so HK, and then K minus, let's do K minus 1 of N minus 1, HK. Up until we get to the N1, actually I need the N1 to compute this. N minus 1, and here I get 0 now. Okay, so what do we know about these ones? These are all R's. Sorry, these are zeros. That's why I computed before. This is 0. Remember the Hn of Rn, the 0 HK of Rn is 0 for all of them except for K equals 0. And here I will have something else with Rn for N minus 1. So it's always 0 unless N is big, unless N is small enough. So I get 0 here, I get this. So these mean that these two are going to be isomorphic. So H, and I can do that for every K, right? Because it's N minus 1. But then I look at the previous one. Okay, no, let's leave it like this. Sorry. H N minus 1, isomorphic H to the N, S to the N for every N. Like this. And again, for this one, I can just look at connectedness. These are all R. And so let's look at degree 1, for example. Here I'm going to have R. For degree 1, I'm going to have H1 of Sn. I'm going to have H1 of R. So it's going to be 0, plus 0, S plus 0. And here I would have, give me 1 second. So I have R, I have H1 of Sn, S plus fine. We're gonna have 0 here. R2, R0. I have this one, and then for degree 2, for example, I'm going to have all zeros. It's going to be, if I look at degree 2, for the n equals to 2, for example, I'm going to have, let's do 3. So I have 3, I'm going to have H2 of Sn minus 1, H2, and then I'm going to have a bunch of zeros. Should be able to get a 0 here somewhere.
I think the point is that like once n is bigger than 0, like the RDN term, that's going to be 0 everywhere. So you just have a bunch of like, for each k, you're going to get hk minus 1, Sn minus 1 isomorphic to hk sk. With that one union.
Yeah, you're right.
And so by induction, if like Sn minus 1 has all, is only non-zero in 1 degree, then you just like bump that degree up by 1 using the microsource.
Yeah. Okay. So yeah, so this is how it looks at every degree. So this is for every k bigger than 1. Or equal to 1. Okay. So we get that these two are isomorphic for every k bigger than or equal to 1, and we need to know what the h1 is. But you can get that from sorry.
Yeah, just because like the first 3 terms are always short exact.
Yeah.
Yeah. It's like more convenient to use the reduced Meyer-Pistorius sequence so that those terms are even there.
Okay. So yeah, going back to it. Okay. So let me rephrase this nicely. Okay. So this part here, okay, yeah, let's just look at it. So this part here, this forces, by definition, okay, you're going to have h1 Sn is going to be isomorphic to R mod the kernel of R2 into R, but, sorry, kernel of this. But you can use the exactness of that part, of the first part, and you're going to have 0 here. In other words,
if you want to say image there.
Sorry?
If you want to say image there to the kernel.
Oh yeah, sorry.
You just have to show.
No.
Yes.
Yeah, but you use it afterwards, right? You have the kernel here, because by definition this is for isomorphism theorem, right? First isomorphism tells you that this isomorphic to this mod. Oh, sorry, the kernel of this one, sorry, yes. No, you're right, this should be image. I jumped a step ahead. It should be kernel of R into H1, and then you use the exactness.
Yeah.
R2 on R, but that's surjective to the 0. Just by computing that thing. And then you get these ones. So if you do, then you use induction, yeah. So you just have to compute for S1. And once you know S1, you can go for the other one.
It still works for S1. You just have to like be careful that the zeros don't interfere with your argument. No, yeah, it is. You do have to be a little more careful because the sphere 1 0 lower is the 0 sphere.
Yeah.
So like it's not the same pattern. You have 2 components of the intersection instead of just 1.
But I think, but you can get like, oh yeah, sorry, for n bigger than 2 equals to 2, sorry. Then you need to compute, you only need to know the cohomology of S1, and then you can get the other ones, right? Because you don't need the, sure, you cannot do the, you cannot compute S1 using the S0. You cannot do that, right?
Yeah. You can do it with the Meyer-Pistorius sequence.
Well, I guess.
Not using direct cohomology, I guess, right? But
yeah, I think you have to be a bit careful. But you can compute explicitly. You can compute explicitly using Meyer-Pistorius. I guess you would reduce that because it would still be contracted. But the way you do it for the circle, you have these. Right, the same thing. You use these ones. You use them like this. Yeah. You use like this. And I guess the instructions are going to be these two. Okay, so you can use this Meyer-Pistorius. Yeah, no, it's fine. You're using the wrong. Yeah. Right. So then you use induction. You can show that these hk s to the n is going to be equal to 0 for every k. But it uses r for k equal to 0 or n, and 0 otherwise. Just wasting induction now. Not worse. Perfect. Okay, so one computation so that users can be happy. Yeah.
In that the homeomorphism is homeomorphic to S and minus 1 should that be
Yes. Yeah. Sorry, I use equal with a squiggly line for homeomorphism and just one single line with squiggly for homeomorphism.
Because when you said it, you said homeomorphism instead of homotopy.
I think I said homotopic. Doesn't matter. In any case, it's homotopic. It's not homomorphic. Okay. So that's cool. Now let's actually, I want to keep this one here, and I'm going to erase the example, if that's okay. Because I need to use these to generalize what I want to say. And now the idea is to construct what check cohomology is using this intuition we have. Okay, so what are the ingredients we needed to make this cohomology theory? We needed an open cover, and although a little bit more hidden, we needed this sheaf here. So sorry for walking back and forth. But that's kind of boiled down the argument into a nicer description, or more concise. So we're going to rephrase this. We're going to follow. So what we have an open cover that U, which in my first case was U1 and U2, which was U and V, but let's just write it as UI, or I from it. We have this open cover. And okay, so that's open cover for M, and this time we have sheaf and we had omega 0, omega 1. Okay, just if you want to know what a sheaf is. More or less, very basic. Yeah. Okay, that's intuition is all you need.
Okay.
Like I'm not. You don't need to know many details. Like even in this case, you don't need a full power of sheaf. For example, just think of a pre-sheaf, which is for every open set. I assign this a Beating group or a ring or module, and have restriction maps. That's all you need. Just a functor from category of open sets into a category of Beating groups. Okay, now this open cover, and what I also have is this, from this open cover I can define intersections. So for notation we let U of I sub 0 up to I sub k to be the k-fold intersection U I sub 0 intersection U I sub 1 up to U I sub k. This is my notation. And okay, so we have this. And what are we going to do now? Okay. What I did there is I took my omega 0 and evaluated at first at M. Then what I did is I summed with U sub 1 and U sub 2. So I had this sum between, so let's do omega, let's do k, this is for any general k, U, I sub 0, sorry, let's do 0 and 1, I, U 0 plus omega k, U1. When these are all the elements that I have in my open covers, so this really is the product over product of omega k, U I, where I is my index set, In my case, I had only 2, but if I had more, that's how I would probably try to generalize. And then I have this other one. Now I have, here there's only 2, so I can only take one single intersection. But if I would like to take more intersections, I'm going to have omega k of u0 intersection u1. If I would like to take more intersections, I would have to take the sum over all the different intersections I could have. But this really is ui1, ui0, ui1. And I would have the k-fold intersection of ui0, ui1. And then I had a 0, but I had a 0 here, but if I had more, maybe I would have more. Okay, so let's keep that in mind for now. Let's not delve too much into it. And let's keep going through with what I did afterwards, which I guess I erased. So I have this on, we're fine.
Okay. And then, sorry, just the map, you're just doing it in each component the same way you were doing over there.
Yeah, so it would be restrictions, right?
Yeah.
So the horizontal maps were all restricted to each one. And here I would also get the restriction map. I would just do it on each component. And again, note that when I do this, like, first, I'm not going higher in degree. I'm staying the same degree all the time. I'm in K. I haven't looked at what happens if I have the interior derivative, but all I needed here was really just the sheaf, the pre-sheaf, right? All I need is how to take intersection, and I can keep taking intersection on each component and so on. So that's a nice little thing. And then we want to motivate the following. Okay. So how do we generalize this further? So this was the rephrasing, and here I had 0, but so I had 0 here, but maybe I could not have 0. So let's actually do something cool. Is to generalize this. I think the main setting you want is just the topological space with that's Hausdorff and very compact. Maybe just very compact should be enough, but in our case we're just going to stick with manifolds to make sure. So if I write this in a different way, I have my space M. I have the inclusion map between, I can take a union or I can take just a full union, doesn't matter. So that's M topological space, or M a manifold. I have an open cover U of my manifold. And I can look at the following inclusions, and then I can do two-sided arrow, two different arrows for I0 alpha 1, U alpha 0 alpha 1, and I can do triple intersections. So on, I can do 4-fold intersections and continue all this way, depending on how many I have. All I need is my eye to be a directed test so I can take these doesn't or equal signs. Yeah.
So when you have 2 arrows, so your intersection is intersecting 2 sets, and you have that component gets mapped to each of those 2 sets?
Yeah, so these are inclusion maps. So I have U0, U alpha 0, alpha 1. I can either include into U alpha 0 or into U alpha 1. And each arrow is going to be either I include it into U alpha 0 or do I include it to U alpha 1?
And that's why you have the ordering alpha 0 left and alpha 1, so you know which one's left and which one's right. Yeah.
Okay. That's one way to look at it. And there's the easier way to look at it, which is more combinatorial, is that it tells you which one to omit. So the cool thing about Sheaf Cohomology is that even though it's more complicated in terms of this, it's actually a lot more combinatorial. Because what it allows you to do is if I were going to omit alpha 0, it's going to omit alpha 1.
Like your triple intersection, you're mapping into the possible double intersection.
Yeah, exactly. And I think you can make this more precise by omitting by looking at the nerve of the open cover. You can actually look at it as a kind of simplex thing. Yeah.
So what's the definition of that backwards cut?
That's a disjoint union.
Oh, okay, sure.
Yeah.
And I didn't quite understand the arrows.
Sure. So for each, so remember that alpha 0, alpha 1, that really is the intersection of alpha 0 and alpha 1. have two inclusion maps. I can either include it into U alpha 0 or I can include it U alpha 1. So I have two maps, I sub 0, I sub 1. And this is my I sub 0, I sub 1. It's really telling you where to include. And same for general. General, I'm telling you if I have triple intersection, to which of the two intersections do I go to? Or which of the three?
Okay. And so I can get that, but what does it mean when we have like the sequence of arrows and arrows?
Oh, that just means that I have two families of arrows I can choose.
You can either choose.
Oh.
Yeah.
Okay, okay.
I have I0, I1.
Sure. Okay. Okay, thanks.
And now that I have this whole thing, and still we have to always have this. Now given a pre-sheaf, F on M, I can apply my pre-sheaf to get the other way, a sequence in the other direction. So pre-sheaf often do in groups or rings or whatever. So we have F of M, and I have two a single map here to the product F U alpha 0. I'm going to have two arrows, the product of F U alpha 0 alpha 1. Where the arrows are now by just applying my functor to I0 or I1. We'll talk after. We'll talk after. All right, but this is a lot. I have a lot of arrows. Now I want to reduce it to like less arrows. How do I do that? Well, just like I did here, I took the difference. I took these two, which are each one of the inclusions, and I took the difference of these two inclusions. I can just take a sign difference of all my inclusions in each set. So we can define this, and we're going to make a complex now with this. So let me erase this. Man, too much categorical language. So what I'm going to do is I'm going to make a single sequence into the product, the 0 in I, and F U alpha 0, have a single one into product, so 0 less than alpha 1, F U alpha 0 alpha 1, and so on, in just a single set of arrows. Where now my new maps are going to be, I'm going to call them delta. This one I'm going to call R. But where delta is the difference with sign degree, Q of F of IQ, or 0 up until whatever degree I'm going for. Okay. So more specifically, if I want to look how this acts, if I have some omega in the product of F U alpha 0 alpha P, then omega has components alpha 0, alpha P for each choice of alpha 0 to alpha P, and I'm going to have delta of this. Its components in the P plus 1, alpha P plus 1, is going to be the sum. Sorry, here I meant the, I know this one. It's going to be minus 1, the cube of omega alpha 0, and I'm going to omit the cube 1. So this defines a form on the other side. And you can show that, so with this, since the sign is, the sum is sign, you can actually show that delta squared is equal to 0. Yes. Just by computing that. And that means we have a differential complex, chain complex, co-chain complex. So because of that, we can define a cohomology for this chain complex. All right. So we have a chain complex, which one is known by CT, depends on my open cover and on my sheaf, together with my differential map, delta, where this part here really is the K subproduct. The P subproduct. And this is the check complex. Of the open cover U with coefficients with values in the pre-sheaf F. And I can look at its cohomology, which is going to be HP of U comma F, which is the check cohomology of the open cover U with values in F. So this depends on the open cover, which is good if my open cover is nice, but again, for every space choosing an open cover, this is not well defined, right? I don't want to depend on an open cover, but by taking refinement, I can just take a direct limit, and then I have a well-defined cohomology. So, what do I mean by that? If I have a refinement, so this is the check cohomology. Of U with values in F. Okay. Now, if I have if V is a refinement of U, what does this mean? We have a map, so let's call V Vj with index at J, and this UI with index at capital I. We have a map, a set map from J into I, such that V of J is expected to U by J. That's what it means to have a refinement. Are we okay?
Okay, I have a question.
Yes.
I should have asked this a while back, but those pies, to double check, what are they?
Sorry.
What are the pies?
Oh, pi is the product.
Okay.
Yeah, sorry. It's a big product of all of these.
Yeah. I just wanted to double check.
Yeah.
Okay. Thanks.
So this is what a refinement really means. And if you have refinement, actually the cool thing is we obtain a chain map versus using a map, phi numeral from the Q's degree complex of U F into the Q complex of the open cover V by simply taking if I have a form omega in here, and then look at image, it's going to be on an open set here. So if I look at it in the open set, J0 up to JQ, it's going to be omega in the open set that it maps to. So U of phi of J0 phi. That makes sense? So we have this map, and also it's a chain map, so it commutes with the differential complex. Simply because all these are just restrictions, so not really there's anything particularly interesting. And not only that, so this good means in particular, it means we have a map cohomology, check cohomology from HK cohomology map into HK cohomology of open cover B. So let's take refinements. I'm going further down into the chain. And like I mentioned, for manifolds we have this really nice open cover, good open covers which are cofinal. So in particular, if I choose a good open cover, that's where it's going to end. But in general, it might not end there. But
I think it ends if you compute the correct thing.
yeah,
It's like you can still take, once you have a good cover, you can still refine further, right? And the check cohomology is telling you to still follow those refinement arrows. It's just that whenever you get a good thing, it's like that is what it's like.
But like for any topological space, you can always like it's always every open cover like has a like you always limit always going to exist. You can always take its reg limit. Is it always going to be like can you have an open cover that was like host check cohomology of that open cover is the same as the check cohomology of its reg limit?
I think so. Like, isn't that what good covers like do?
Yeah, for manifolds, yes, but I mean for general topological space.
Yeah, I wouldn't be completely sure. I think as long as those contractibility conditions are all in place, then like, it should work out as well as it does for good covers and manifolds. But I'm not totally sure.
All right. Yeah, because to me, I know for manifolds it works, and for every space that I've considered works, because I don't deal with that spaces. But I don't really know. Yeah. Okay. Well, we generalize that pretty nicely. And so, like I mentioned, we want to take a direct limit. You have a question?
Yeah. You said the top line the intensity U are those that means that's what we mean by we have a refinement. Should those be like the unions of those?
Okay. So these ones are the open covers.
Yeah.
So V is an open cover, U is an open cover.
Yeah.
By a refinement, I mean this map from J into I that satisfies this property. If you give me a J, then I can find a U in here that VJ lies.
Yeah. And what are okay, and like fancy V and fancy U are those things there, and what are VJ and UR?
So VJ, so the fancy V is an open cover, so every element is an open set.
Yeah. Right.
So VJ is an open set.
Okay.
Whose union is all of them.
Yes.
That's an open cover. It has to cover all of them.
Yeah. Okay. Good.
Yes. And same for UR.
Okay. Perfect. Thank you.
Okay. And actually, fun fact is also if you have these two open covers and you have two different refinements, then the the corresponding 5 stars are actually homotopy. So that's pretty simple. So that's pretty good. In particular, you may define the same map in cohomology. So the whole goal of this thing is that I can take a direct limit. So definition, the check cohomology M is H star with values, so it depends on the sheet, with values in F, is going to be the direct limit over all open covers of the distinct check cohomology covers. So again, with when when you have a manifold and you have a good cover, if you manage to compute it to a good cover, because they're full final, you only need to compute a good cover, that's going to give you the original one. Give you that. For more general stuff, I cannot really tell you because I don't deal with that. But a cool fact, so once you have this is now independent of whatever open cover. It only depends on my pre-sheaf F. And why would I make you go through all this hassle of generalizing the other thing? Is because actually this doesn't give you any new information for a math. At least if you choose F right enough. So more specifically what I'm trying to say is the following theorem, which is also how you prove that manifolds are pretty nice, is if you let R be the constant pre-sheaf, then the cohomology of the constant pre-sheaf is isomorphic with the round cohomology. And I think that's how you prove the Durand theorem for like a bunch of different ones. You prove that so there are many ways to prove this, but one of them is to prove that they're all isomorphic to the cohomology of the constant pre-sheaf. And so if you look at the singular cohomology, one way to prove that it's actually the same as Durand for over R. So yeah, you can choose F to be a variety of things. For here, this one here is actually if you choose F to be the sheaf of differential forms, where you can choose to be infinity chains, and we got cohomology of that, so singular chains, and a variety of other things. For nice enough stuff, you kind of cut it easy
about that part. So you said that you could reconstruct the Durand cohomology groups by taking sheaf cohomology with the sheaf of differential forms. That's what you said?
Yes, I believe that's what I said.
And then that's the same as just using the constant sheaf R.
Yes, the idea is because, okay, there's a bit of subtlety there. The idea is because the way you do it, you have a resolution. You can make this resolution, like you have this double complex, make this a resolution, you can show that this, like one part here is actually going to be isomorphic to the other part. You have this double complex. I'm not sure if the wording that I use is correct, but I'm unable to find I'm going to find both a proper argument or a counter example. So,
did you get this from Boston too?
Yeah. Okay. That's where I learned most of my
languages like I've seen before.
Yeah. So yeah, it's a nice book. But let's do something different. So yeah, again, so something interesting about this whole thing is that if you look, when you look at the Durand cohomology, so again, we looked at how, if you take this exterior derivative, you go to k+1 forms, or you can go, like, images of k+1 forms, and so on, of k-1 forms. So kernels of k forms k+1 form, mod the image of the k+1 forms. But here, we actually just use combinatorics. It doesn't rely on knowing what the exterior derivative is, and so on. But the proof of this does rely on the exterior derivative. It relies on making what I said. You have this resolution, you can make it, and then you can show that these two are going to be isomorphic. So you do actually need the exterior derivative, but this is very combinatoric. So you don't really need to know much differential geometry to compute this. And that's pretty sweet. But let's actually make a nice construction now that we know check cohomology. And we're going to tie it up to our knowledge of line bundles, or bundles that we've learned so far. And in particular, I'm going to be using line bundles. So there's this big theorem about classification of line bundles. In manifold theory, you can have line bundles, they actually form a group. If you have two line bundles, you can take the tensor product, that's the product. You can use a new line bundle, and so on. So that's pretty sweet, right? So again, that's an application. Application is the classification of line bundles. Okay, so again, M is my manifold, and Lm is going to be the space of all line bundles. Over M. And I'm going to mud out by equivalence. So we know what equivalence of vector bundles are. Talked about this before. So let's look at this moduli space. The moduli space of all line bundles over M. Modular equivalence. And the goal of today, of this part here, is to show that. So again, this is a group. This is a group with the product. So the product multiplication in the tensor product of line bundles. The identity is a trivial line bundle, and if you have a line bundle, you can find an inverse. And the goal of this thing is to show that actually this moduli space is isomorphic to the second check homology of a given sheaf. So we're going to go for that. Okay. Give me a second. All right. So we have the line bundle. So we have this line bundle. So that L B is going to be an equivalence class. So this is my equivalence class in this moduli space, but let's take a representative L. Now, so let this be there, and UI SI is going to be a local trivialization. Okay, and for L, such that let's assume that UI is the cover. So again, if you pick any trivialization, I can take the open cover, refine it further, and then just take a restriction of the SI, so I get that trivialization with a good cover from my manifold. Okay, so that's pretty sweet. And once you have this, so these are the trivializations. The SI define transition functions. So actually here it's going to be complex. Complex line bundles. Complex line bundles. These are going to be, we're going to find transition functions Fij from the intersection Ui intersection Uj into the complex numbers. Tij. So you have these transition functions, right? Now what we're going to do is we're going to construct a new set of functions. Which I don't think are going to look like. Yeah. We have these transition functions.
There's even more. There's a non-zero complex as well, right?
Yeah. All right. So once we have this, we're going to define Fij to be equal to 1 over 2 pi I, then the log of the transition functions. Take any branch of log you like. Okay. So again, these Tij's satisfy the co-cycle condition. That's what William did a while ago. He showed that. So since we have that Cij, Cjk equal to Cik, what we can do is then, if I look at e to the 2 pi I,
Give me 1 second.
e to the 2 pi I of Fij plus Fjk minus Fik. What is this? It's going to be e to the 2 pi I by definition of Fij, so we're going to get rid of the 2 pi I. We're going to have log of Cij plus log of Cjk minus log of Cik. Maybe log e of log, I can put this in a single thing, Cij, Cjk over Cik, but this is Cik, so what I get is 1. Which is pretty sick, because that actually means that this thing here, which I'm going to call Aijk, it's actually 6 values instead. But these are continuous functions on a contractible open set. So actually this means that these must be constant. Just reset. So, are we okay? Are we okay?
I think so.
Yeah.
It's just helpful.
Okay, that's pretty sick. So, because of this, I have these functions, and okay.
That's awesome. Holy shit. That's crazy.
So this implies that we have an element such that Aijk is an element of C2 with respect to my open cover with values in the constant species Z. Okay. Now there's the question of, is this a cocycle or not? Right, so let's compute it. I do delta J, and I look at it as
Isn't it already delta of f? So
sorry?
isn't it already delta of f?
Yes, you're right. Yeah. Sorry, it's equal to yeah. Okay, yeah, you're right, yeah. So it's equal to Aijk delta of I call it F. Or F is Fij and Ij, Jk on the left. Okay. So F. Okay. So in particular, this implies that delta of Aijk is equal to 0, and so this implies you have an element A in the second homology.
The zero element.
Sorry?
The zero element. Delta F.
Okay, so yes, that's what I was thinking too.
Yeah. These functions f, I don't know if they're like the same kind of things that you were thinking about before.
Okay, I think I know what the slope is here. Give me 1 second.
So which delta is this? It's from the check.
This is a check one, yeah. So it's simply the alternating for each restriction. Oh wait.
The f's are not defined in all of the...
No, no. I don't think this is true.
Mm-hmm.
This is not true. No. You just have to compute it right away. So you can show that delta Aijk is equal to 0. And the way you do it is you have to just compute it. So you would expand into each one of these, and what you would end up having is you're going to have, these are again, they're just restrictions. You're just going to be restricting the transition functions even further. And once you do that, so you restrict to P. Let's just compute it actually. Because I think that you're just restricted to even further to like a 4 triple intersection. These are all going to agree. They're going to give you a 0. So it's going to be, let's do it actually, Fij minus plus delta Fjk minus delta F on K. And again, the definition is going to be delta. So we're going to have to look at Ijk. This can only make sense in Ijkl. So here we have Ijkl and Fij.
Do you want to use the same letters again, or should they be like 5 different letters?
I'll think the same. The thing is that I was sometimes using the same letters again because you have like, again, these are defined in I intersection J intersection J intersection K.
Yeah.
So I'd have to go into I intersection J intersection J intersection K intersection and L that is like underneath. So I'd have to like, I'll still keep the first two, I would just go to like a further one.
Yeah, okay.
You know, let's not go to the computation, but what happens, I'm pretty sure, is that once you do that, you're just going to be intersecting like these functions further and further to like the same open set, and if you do this alternating sum, you're going to have even more alternating sums, but you're going to start canceling because, again, these are all defined. Like, once you intersect further, these are going to start to agree. That's what I'm trying to say. And so they're going to eventually cancel out. So you will get 0. I think you just have to compute it. It's going to be a bit tedious because I don't think it's worth doing it, but because you're going to have to decompose this into further alternating sums. It's going to be like Ijk without that, and then JKL without that. But you're gonna have the same ones with the other ones here, and eventually you will just kind of like have matching ones gonna cancel.
I want to ask about the saying that AIJK is in this group. That's just like an abbreviation for saying that the product of all of them is in the group?
No.
So the group was the product over all, like alpha 0, alpha 1, alpha 2.
Yeah.
Right?
Oh yeah, you're right.
So each of those
Yes.
would have their own IJK.
Yes, it's right. Yeah, yeah. No, it's an abbreviation. Yeah, sorry. So it would be an A. Sorry. It would just be A, where that in A IJK, like in the IJK.
That is the part of A over UIEJ.
Exactly. Yeah.
Okay.
So define those. Yeah. So let me erase the competition. You can actually do it, but it's going to be very tedious. So I don't recommend doing it. But we ensure that the delta is equal to 0, and then we have a cohomology class. All right. So there's a few things you can show. You can show that first it doesn't depend on which algorithm you choose.
What happens to trying to keep them in separate?
Okay, yeah, we're almost done, don't worry. But yeah, it shows it doesn't depend, it's well defined, doesn't depend on which algorithm you choose, doesn't depend on your choice of trivialization, and actually it's well, again, what we did is we started with a line bundle, we took its trivialization, found the cohomology class, and you can show that it doesn't depend, like it's well defined up to equivalence. If you have the equivalent line bundles, you get the same class. And once you take its direct limit, you can map it further into, sorry, this depends on the complete cover, but you can map it further into the actual check cohomology. And what we define, so this defines the map. Defines the map, which I'm going to call kappa, from the space, the modular space of line bundles into H2. That, where I take a line bundle and map it into the corresponding class, which I can call it A, but this actually is how you define the return class of the line bundle.
Can I ask 4 quick notation questions?
Sure.
You call fancy L of M the modular space, but over there you call it all line bundles?
Yeah.
Modulo equivalent.
Modular.
Oh, and so L of M, the name of it is the modular space of M?
It's the modular space of line bundles over M. Yeah.
Okay. Okay, next. And the C2 use the, what is that?
Yeah. So that's the check cohomology of the open cover U with values in the integers.
And that was the chain.
The two
that was
chains.
like the product over all like double intersection. So. Where here really mean this is really going to be just that, but it's the pre-sheaf. These are just going to be that. There's going to be like an infinite product of. So for each double intersection, you have to secure many options.
Oh, I see, okay. And you call that the check cohomology, but you call that also the check cohomology?
It just depends on what sheaf you're taking. You can do check cohomology for any sheaf you want.
Yeah. So that's for that's the check cohomology with values in F. Now I'm doing the check cohomology with values in Z.
Okay.
But it's on three sheets.
Great. But, I guess, why is it C and not H?
Well, that's just like the co-chain group. That's like before taking cohomology.
Oh.
Yeah, this is the check complex, the
Right.
complex.
Right. No, not the cohomology. Okay. Gotcha. And so, okay. When you have like H star of M and R, what's a good intuition for the second input of H star?
The second input, okay. So, what's a good intuition? I would say the intuition, at least the way that I think about it, is what kind of information are you trying to obtain from your space? If I choose their differential forms, I'm trying to get some DRAM information, some differentiable information. If I choose the complex of holomorphic forms, for example, that's going to be the Dolbeault complex. Now I'm looking for complex information, holomorphic information of my space, and so on. Depending on what pre-sheaf you take or sheaf you take, you're going to be looking at what kind of information you're trying to get from your space.
Okay.
If I want algebraic information, I would choose some algebraic pre-sheaf there.
And like if you write like an algebraic thing with an underlined like a constant sheet for that, that's basically like you're just taking coefficients in that sheet, like coefficients in that group, like in the ordinary cohomology way that we were talking about last time. About just like being able to use those coefficients in your combination.
Right, like Z mod 2, for instance.
Yeah. So if you take if you take F to be some constant pre-sheaf like in a ring, so like Z mod 2, Z mod P, Z, some ring R, then you're really just changing coefficients of your cohomology.
I see. Okay.
But you can take cohomology in a more general pre-sheaf if you want.
Yeah, right, that makes sense. Okay. And last question, what's the direct sum?
What's the direct sum?
If it's 2 involved, then
I think you mean direct limit or direct sum?
Oh, sorry, sorry, direct limit, sorry.
Okay. Yeah, no, that's fine. So, like I mentioned before, so for when you have like modules, you have a directed set, so you have MI, you go into MJ, and so on. Or maybe you go into different other ones. But if you have a sequence like this of modules, you can define the direct limit to be like, the proper definition is going to take the sum of all of these. You're going to mud out by those that have the same image eventually.
Okay.
So you have like here you have a map Fi, here you have Fj, and so on for like as you go along. You're going to take a direct sum of Mi's, I to the next I. You're going to mud out by those that have the same images. So this would be Fij, Ij, then Jk. You're going to choose those such that there exists K such that Fij x equals F Fik Fjk. And this you want to know that eventually there's something big enough where they're equal. That's going to be the direct limit of the yeah. So that was the punchline of the talk, is defining the first Chern class of a line bundle. And that's for at least with all the stuff that I do, all you need is the first Chern class. You don't need anything else. Because as for myself, I never really. I think sometimes I get the second Chern class. That's much like that. I don't need the full power of the theory. But thought this would be a nice place for Daniel to enjoy getting Chern class. But yeah, the cool thing about this, again, you can compute these very explicitly, right? What I gave you is like a very explicit construction. Give me a line bundle, give me the transition function, I define these functions, and then I can just compute it like that. It's not, there's barely anything involved. It's pretty cool. Yeah, that was the goal of the talk.
Where's the NTS singer?
Oh, that's him.
I thought you said you wanted to. For index theory.
Yeah, like I'm okay with doing it, but he can do the full power of K3. Like the one I would have would be the hit kernel approach, which is definitely just for Dirac operators. But I think there's a more general result. The original result was more general using K theory.
Right, but
it was in K theory anyway.
Yeah, but you're going to do K theory, but not index theory, right?
I won't have time in my talk to get things like
right. In my research actually, to use the Dirac operator. I think it might be related, I don't know, or Raza told me anything, but it might be related to studying the spectra of these Dirac operators on either compact or non-compact manifolds.
I see. Yeah, remember when you sent the message, like, I wasn't sure what you meant by the Dirac operator, but they are associated, like, if you have, because to me Dirac operator is a family of operators, like, But once you have like a connection, you have an associated Dirac operator.
The one for the Levi-Civita connection.
Yeah.
The
And that's what I assume, like when you said data, like maybe you have like some sort of structure and there's an associated one that's natural to that.
Okay, that makes sense.
I wouldn't be surprised if it's that.
Yeah.
Yeah, I can talk like if. Well, I'm not sure because it seems like like I can give kind of a. Of course, I cannot prove everything because it's a very long topic, but I can give a talk about that. Just getting to the theorem and applications of it. We have some pretty cool applications.
Okay. Nice. Thanks.
I was just wondering, like, this A equals delta F thing, like, is it not true that A is delta F in this case? Because it just looks like well, I'm not sure, but like, yeah, it looks like it's the alternating sum thing that's going on.
Can't be in general because kappa is an isomorphism, or the bijection, I guess.
Yeah, yeah.
Isomorphism because we have a group structure on the left as well.
Yeah.
Okay, so I have two reasons where I can see it failing. So, let's see. Oh no, no, it can't fall like that. Like, okay, it definitely cannot be. But I think the thing is that, okay.
Is it in general there is no F that's like defined on all of these open subsets maybe?
Yeah, because like these Fij's, right? They come from the transition functions.
Yeah.
So.
And you might have to like pick different log branches for each of them.
Yeah.
I see.
So that's my guess. Yeah.
Okay. I think I see. Because if you can pick the same branch for all of them, then you'd have one function that's defined on all of the open sets that can restrict. But if there's different, you might have to take different log branches for the different intersections, right? Is that how it is?
Like, to me, that's one reason why it could fail.
Yeah.
I think there's something else going on here, though.
Okay.
Because again, okay, this section is let me see. That would mean that if I do that, I'm not sure. I have to think about it. I don't think it's particularly hard. I'm just getting blocked for some reason as to why. But the idea would be that you cannot find a general F that satisfies this. I don't know if the log is the only thing that could fail. I think there's more that could fail here. That just guarantees that every single time we're never going to get it. Or most of the time.
Thanks.
One thing I always think it's cool. So like you start out with this totally smooth stuff, and then you compute. Oh wait, these are actually taking values in Z. So your moduli space is actually a discrete set.
Yeah.
You take it like from like the representability route, that's a little easier because you're taking like homotopy classes of some mapping space.
Okay.
Or like, because yeah, it's just like maps into your classifying space modulo homotopy.
Okay.
So like typically when you take homotopy classes, like that just drops you down to the discrete level, right?
Okay.
But here it's like a weird thing that you compute. I don't think that's funny.
Yeah, to me that's how I learned. Also, because the things you can also relate these to like the way you construct the order class also is pretty similar to this for rank 2 vector bundle.
Yeah, I mean this is the construction of the order class for
like
one. Yeah, for the
Yeah. So for me, like the first thing I learned was the Euler class construction, and then when I read this, like, it's pretty nice. Yeah, this part here, I learned it from Constance, like Bertrand Constance. He has a book or a chapter in the book of geometric quantization, and started with this. Eventually, you do need to know about the Turing classes, and he starts talking about curvature and quantifying them.
Necessarily the book.
Yeah. I think it's a pretty good book to learn about Bertrand Constance. He was one of the founders of geometric quantization, because it was him and think Kirillov also had work on that. This whole thing about the orbit method is complicated matter.
Right.
Eventually, what that's too much complication. Yeah, it's cool.
The college sections.
Thank you.
Getting closer every day to understanding what Witten means by the index of an elliptical operator.
Questions, Danny?
Moduli space of
Oh, that is
the
okay.
I don't